Feel Good Hemp is the first and only brand to offer high-quality CBD oil products alongside a free platform that offers proven self-help and self-healing techniques, all to help you feel good naturally. Feel Good Hemp was started by Noah and his wife Danielle after they used hemp oil and other techniques to save Noah's father from a terminal cancer diagnosis. Now, I heard this story firsthand when I interviewed Noah. It's a real good one, and it's probably the most heartfelt and compelling story I've ever heard about why someone started a CBD company. So Feel Good Hemp is more than just a great place to buy CBD products. It's actually a community of like-minded souls committed to feeling good and doing good. So use coupon code GENIUS33 at checkout to save a third or 33% site-wide on your first purchase. Visit feelgoodhemp.org to shop now and access their free empowerment platform.
Forget frequently asked questions,
common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Foundation. I have Michael Zevin. He's a NASA Hubble Fellow. He's at the University of Chicago. And we're going to talk about black holes and gravitational waves. So, Mike, thanks for coming.
Thanks for having me.
Yeah, if you would, tell me, how did you get interest in black holes and gravity waves, however long ago when you started studying it?
Yeah, so I really dove in at the start of my Ph.D., which was in about 2014, 2015. I trained in physics and astronomy, though there are lots of different pathways you can go down, everything from galaxy evolution to cosmology to studying planets around other stars. But I started doing work in a research group that was interested in these things called gravitational waves. And these may have not been very well known to the general public at the time, but I joined this collaboration called the LIGO Scientific Collaboration in summer of 2015. This is 15 years after this collaboration started looking for these signatures of ripples in the fabric of space-time. And luckily enough, a few months after I joined, after 100 years of predicting these things that date back to Einstein's formulation of general relativity, his modern theory of gravity, we found the very first signal in September of 2015. So this is pretty profound because for the majority of astronomy, virtually all of it, we really are just observing the universe with light, so electromagnetic radiation, whether it's the light that we can see with our eyes or infrared light, X-rays, gamma rays, ultraviolet. They're all different forms of the same phenomena. And now we're starting to be able to look at the universe and really listen to the universe in this completely unique form of information, which is called gravitational waves. So that's how I got the start. And then over the past half decade, fields really flourished. We now have almost 100 events that we've observed in gravitational waves. And the things that we see are typically very extreme objects. So when two dense stellar remnants, things like black holes or neutron stars, find each other and rapidly merge and emit a huge amount of energy in these gravitational waves.
What is a gravitational?
Yeah, so gravitational waves, so they're a little bit different than sometimes people call them gravity waves, but they're actually two different phenomena. Gravity waves are waves where the restoring force is gravity itself. So in fact, a water wave on Earth is a gravity wave. Gravitational waves are a completely different beast entirely. So these were predicted by Einstein back in 1916. And the reason that they came about had to do with his theory of general relativity. So people may have seen kind of cartoon schematics of this theory, but the idea is that mass and energy, things like planets and stars, interact with the fabric of space-time itself. So said very precisely, mass tells space how to bend and space tells matter how to move. So you might have seen kind of a picture of looking like a trampoline, elastic fabric of space-time, and when some massive object like a star is sitting on it, curves that fabric around it. And that's what gives us the phenomena that we know as gravity. Now, similar to if you were to drag your finger through a pond of water, if you have objects that are moving or really accelerating through this malleable fabric of space-time, they emanate ripples that propagate on the fabric itself. And these ripples are what we call gravitational waves. Now, when these came out of Einstein's theory, folks thought that it would be near impossible to ever see them because their signals are just so infinitesimally weak. But 100 years later, we actually have the technology to be able to observe these and use them to learn more about kind of extreme environments across the universe.
But what does that mean that a gravity wave is given off? If an object gives it off, what happens to the object? Is it, was its mass suddenly reduced or converted into energy, and that's why a gravity wave was emitted for conservation of, some conservation law, or what's the reason?
Yeah, so it's a little tricky to explain, but you're right on the point here. So if you remember Einstein's famous equation, E equals mc squared, so there's this equivalence between matter and energy. Anything that has mass, that has weight to it, holds on to some energy itself. Now, as they're moving through this fabric of space, they're emitting energy, they're losing energy, whether it's orbital energy or their mass itself, to these ripples in the fabric of space. So what's really amazing is the things that we're best able to see now are collisions of black holes. So these are compact objects that are tens, maybe even up to 50 times the mass of our sun. And when two of these objects get closer and closer together, they're emitting so much energy in these gravitational waves that we're actually able to observe them here on our planet Earth. When the two objects merge, the sum of their masses is actually significantly less than the sum of their individual masses before merger. So for the first event, for example, it was the merger of two black holes about 30 times the mass of the sun. This is the first event that we saw. And to be precise, one was 29 times the mass of the sun, one was 36 times the mass of the sun. And we can tell this by the signals that we get here on Earth. And when the two merged, the remnant black hole that was left over was 62 times the mass of the sun. So if you do a little math in your head, you'll see that 29 plus 36 is actually 65. So there are three solar masses of energy that were emanated away from the system in the form of these gravitational waves. And that's a ridiculously massive amount of energy, actually. That solar masses, if you convert that using Einstein's E equals mc squared, actually turns out to be more energy that's emitted than what's emitted by every single star in the observable universe for that second of time. So These are really extreme events. The problem is space itself is really stiff. It's really hard to make wiggle. So you need to have these incredibly energetic events in the universe to be able to give any kind of signature that we could possibly detect here on Earth. Anything that's moving in the cosmos, from me waving my arms to the Earth going around the sun, is emitting these gravitational waves, but just such weak gravitational waves that we'd never be able to detect it. We can only see it from these really extreme collisions out there in the universe.
How could mostly vacuum have a stiffness or a pliability to it? What is the fabric of space-time if it's vacuum with particles winking in and out of existence? Like, how do you establish the properties of it? How did someone characterize that?
Yeah, these are tricky questions, and you're asking some really intriguing stuff. So the stiffness is really kind of just a term that I'm using to say how easily you can impart energy into the fabric of space. So it's not something that has mass or light or anything like that, but with the universe expanding, space is a malleable thing itself, and there's this interaction between objects in it and that are moving through it. So these gravitational waves act similar to light in that way. They're not massive at all. They travel at the speed of light as well. So this kind of cosmic speed limit. But when you plug in kind of these constants in our universe, like the gravitational constant and the speed of light, these things that kind of govern the relative strengths of all different forces in our universe, it turns out that these gravitational waves are just incredibly, incredibly weak relative to other kinds of phenomena. So it's not like you're wiggling a fabric itself, but it's just kind of propagating through this space-time fabric.
Well, as a gravitational wave or any electromagnetic wave traverses space, can you tell anything about the nature of the fabric of space it traverses? Like if it hits a patch that is more empty than another patch, or more, has more stuff in it, does the electromagnetic wave get altered, redshifted, slowed down? What happens? Same with the gravity waves.
Yeah, so they both suffer from redshifting. That's a natural consequence of our expanding universe. And that means that as light or these gravitational waves are propagating at some frequency, as the universe is stretching, that frequency gets stretched out as well. So they push to longer wavelengths and lower frequencies. However, unlike electromagnetic waves, gravitational waves interact very, very, very weakly with any kind of matter. So if you're looking at a distant galaxy, if there's all this dust in between you, if you're looking with your normal telescope, you're going to have interactions of that light with all that dust in between the galaxy and you. gravitational waves will pass right through that dust and not care one bit. So that's a good thing because they're relatively kind of pure phenomena in the universe. But the bad thing is, since they're very bad at interacting with material, with any kind of atoms or dust or anything, it means that they're very, very hard to detect themselves. So the good side is that we can kind of look back to even earlier in the cosmological history than we can with light. So light used to be trapped up in the early universe because things were so hot and dense and they were interacting with particles. But these gravitational waves were not. When they were set free in the early seconds of the universe, even early split seconds, they have been traveling pretty unperturbed since then. So we haven't detected these yet, but with our ideas of how the universe began and the theory of inflation, so this really rapid expansion of the universe within the first split second of its existence, it should have emitted gravitational waves, and those are something that we actually look for and are hopefully going to find in the coming years, either seeing the signals of the gravitational waves themselves or the effect that they have on light, for example.
Supplementing with hemp CBD products is one of the best things you can do for your overall wellness or to improve conditions like chronic pain, sleep issues, anxiety or depression, or other conditions related to inflammation. Feel Good Hemp offers high-quality CBD oil products alongside a free platform of proven self-help and self-healing techniques, all to help you feel good naturally. They're offering our listeners a very generous 33% off their first purchase. Use the coupon code GENIUS33 at checkout, and you'll save 33%. Visit feelgoodhemp.org to shop now and access their free empowerment platform.
Can you place them on the electromagnetic spectrum? Do they have a frequency and an amplitude, and what constitutes the amplitude? And again, where does the frequency lie?
Yeah, you totally can. The spectrum is a little bit different than what you have with electromagnetic waves. So you might know that, for example, the light that we see with our eye are hundreds of nanometers. So 10 to the minus 7 or so meters. The gravitational waves that we're able to see with our ground-based detectors right now, the ones that are the workhorses, have frequencies in the range from about 10 to 1,000 hertz. So that's quite a bit larger frequencies than we have for electromagnetic waves. But just like electromagnetic waves, there is a whole spectrum of these gravitational waves that we plan to detect. The ones that we see now are really on the highest frequency end of gravitational waves. So think of them similar to, like, we're able to see the gamma rays and the X-rays, these really high frequency kinds of waves and gravitational waves. We really can't see anything lower from Earth very easily because of the way that we detect them. So we detect these gravitational waves by seeing how they stretch and squeeze the fabric of space that Earth is sitting on. So we essentially design very, very precise rulers that can monitor and detect these tiny stretches and squeezes of space itself. That's the effect that they have as they pass through. But Earth is a living thing in some sense, and it's always moving and rumbling. And in fact, the seismic noise, the noise that we get from just the Earth itself, really limits what we can see below about 10 hertz. There are the next kind of generation of missions are going to be doing the same kind of observations, but from space. So we're going to be sending these very precise rulers into space where they're not affected by all of the terrestrial effects that make it hard for us to see lower frequencies. So whereas LIGO, the instrument that I work primarily with, sees frequencies from about 10 to 1,000 hertz, these space-based detectors, so LISA is the one that's going to launch in the 2030s, is going to be sensitive to the millihertz regime. So seeing frequencies that are around 10 to the minus 3 hertz or so. So whereas we are able to see up from the ground what we call stellar mass black holes, these black holes are the remnants of stars, from space, you're actually going to be able to see more massive mergers of black holes. So mergers of supermassive black holes, like the ones that reside in the centers of galaxies. Yeah, just like electromagnetism, there's a wide range of frequencies that we can observe these at, and all these different frequencies are going to unlock kind of different aspects of these extreme mergers in the universe.
You said they don't interact, or they interact very weakly with pretty much everything. I don't even know how you'd figure this out, but does anyone theorize that the gravitational waves interact with dark matter?
Yeah, I'm not too aware of any theories of interacting with dark matter. Dark matter in itself, if you kind of are a fan of the WIMP theory, that these are these weakly interacting particles, then dark matter itself also interacts very weakly with everything. So probably not is what I would say, though I'm not familiar with any literature that suggests that. But there are other, these are kind of dated theories of dark matter now, but back in the day, people thought that dark matter might come from lots of massive dark objects in the halos of galaxies. So things like black holes and dim stars in the halos of galaxies that are adding this extra mass that we can't see with light. And if they were black holes, then, we could see these kinds of things with gravitational waves. But as of now, that theory is kind of fallen wayside because searches for these types of objects have kind of come up fruitless.
When you talked about gravitational waves, slightly stretching and I guess compressing space as they move through it, is cosmic inflation linear and constant, or is it pulsing as well? Does anyone know anything about the inflation and the stretching of space-time? What does that look like?
So do you mean the initial inflation that happened in the early epochs of the universe, or the expansion that's going on now?
Yes, the stuff that's going on right now. Is it pulsing? Is it accelerating? Is it linear? How is it characterizable?
Yeah, so the running theory now is that expansion of the universe is in fact accelerating. So I'd say that's a pretty a theory that's well founded by observations as well. So this was back in the early 90s, that as the universe grew and grew and grew, eventually started expanding faster and faster and faster. That aspect, as far as I can tell, isn't something you'd be able to observe in gravitational waves. Definitely not anything that the ground-based detectors that are currently running could do. But the early inflation of the universe that expanded the universe much faster than it is now is something that could leave an imprint with gravitational waves that people have been looking for. So something that was, you might have heard of something called B-mode polarization in the cosmic microwave background. This is kind of a unique signature of that gravitational waves have from that early inflation of the universe. And that's something that people are closing in on possibly being able to detect, which is another kind of indirect observation of gravitational waves, because you're seeing how they affected some of the light in the early universe.
In the detectors that would detect gravity waves, you have detected them from, let's say, collisions of two supernova or black holes merging? Have there been any? There have been some detected, like you said, the higher frequency range, right?
Yeah, so as part of the LIGO and Virgo collaborations, there's also a detector in Italy that's working with the two detectors that we have here in the US. And just recently, we actually published our third catalog of these types of events, which has brought the total number of events up to 90. So we're almost at the 100 mark. And the events that we're most sensitive to see with these types of detectors are, like I was saying earlier, the mergers of two compact objects. So most of the events we've seen are the mergers of two black holes, but there are a handful of events where we've seen merging neutron stars as well. So slightly less massive stars than the ones that form black holes will leave behind a dense core called a neutron star. These are objects that are about as big as a city, so maybe about 10 miles across, but more massive than, for example, our sun. So they're incredibly dense objects. And if you piled a little more material on them, they could collapse into a black hole. The benefit of these neutron stars is when they collide, unlike black holes, they also emit a significant amount of light as well. So luckily enough, the first merger of neutron stars that we sensed with our gravitational wave detectors, we were actually able to see the explosive event that occurred simultaneously with it. So this was an event called GW 170817, and this explosion that we call a kilonova is really interesting for a lot of reasons. One is because these types of events, these kilonovae where you have two neutron stars merge, are likely responsible for producing most of the heavy elements that we have here on Earth and in the universe. So things like platinum and gold and uranium. And in fact, this one single event synthesized a little bit 200 times the Earth's mass in gold. So it's a very rich event. And this event, the explosion peaks and then transpires over hundreds of days. So it was followed up by hundreds of telescopes around the world. And in fact, the paper that announced this particular event had something like a third of all astronomers on it as co-authors, because there were just so many cooks in the kitchen from the gravitational wave side, telescope follow-up side, that it was just a really kind of profound and impactful observation and discovery.
Question. So if I have a gravitational wave detector set up, I would think that it would be a good idea to set up other experiments like in the immediate vicinity. So when a wave comes in, you could maybe timestamp the other experiments. Like, let's say I have a little vacuum chamber set up and I'm looking for like changes in the Casimir effect, and a gravity wave comes in. We finally got one. We observe it on our detector. But again, I have all these other experiments running at the same time. And again, with a timestamp, I can look at that exact moment. How are they affected? And maybe then I could know the effect of gravitational waves on other systems.
Yeah, that's a great point. In fact, there are hundreds of other sensors that are operating at the same time as the main sensor that's detecting gravitational waves. Those aren't really observing for new kinds of physics or anything like that. But since these signals are so weak, we have a huge amount of noise pollution in our detectors themselves. Now, having two detectors, so there's one living in Washington State and one living in Livingston, Louisiana. Having two detectors is kind of a first order check to make sure that something is truly astrophysical, because these things are separated by a couple thousand miles. The light travel time between these two detectors is about 10 milliseconds. So when we see one signal in one event and see the same kind of signal, one signal in one detector and the same kind of signal in the other detector, and the time delay between them is less than 10 milliseconds, that's a good sign that it's of astrophysical origin. Whereas things like big gusts of wind or earthquakes across the planet or magnetic interference would likely only affect one of the detectors within that kind of small time window at a time. The other things that are kind of occurring at the same time, so these are all timestamps, and it allows for our telescope partners, the people that are looking at light from the universe, to follow up in the regions of the sky where we triangulate these systems coming from. But for example, for this one event where we saw this explosion in light, this kilonova alongside with the gravitational waves, the first light that we got came less than a second after the gravitational wave event. And this put very strong constraints on the propagation speed of gravitational waves compared to the speed of light, because they traveled hundreds of millions of light years to get here, yet the gravitational waves, the light, came within such a close time interval of each other. That you can put some very strong constraints that the gravitational waves must be traveling very, 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 very close to the speed of light, if not at it. So that's some kind of a joint science that you can do by timestamping these particular signals.
So does anyone have, again, an experiment that can characterize on Earth what a gravitational wave would do to vacuum? And I know we can't do super high vacuums here compared to space, but has anyone set up an apparatus like that, and was anything observed?
So the gravitational wave detectors that we have here on Earth actually do operate in a near vacuum. I don't know exactly what the pressures are, but you need to have the laser light that's doing the measuring of distance be very, very, very pure. So the tubes where these lasers are going down are actually operating in near vacuum. But if you're talking about something like analogous to the Casimir effect, for example, I don't think that's something that, well, at least I don't know of any experiments that are currently looking to see how gravitational waves could impact that, though I'm far from an expert in that stuff. I'm more of a astrophysicist. So I study more so the systems that give us these gravitational wave events and how gravitational waves can kind of inform them.
Gravitational waves, I mean, are the lower frequency ones, is the belief that that's what conveys gravity? Or are waves a completely separate phenomena from the phenomena of gravity of a mass acting on other masses?
So you mean, are they kind of the information carrier of gravity, similar to the graviton?
Yeah, like, I know people have proposed the graviton, but I don't know, the gravitational effect right now, I'm standing on the Earth, I'm standing on the ground. The gravity that I'm experiencing, is it through very low frequency gravitational waves? Is that how gravity is affecting my atoms? Or like, how do you think gravity works normally? Which I know is also a real easy question too.
Yeah, we know if we believe Einstein's theory that gravity does obey this kind of cosmic speed limit that light and information does as well. And that would mean that it has to have some kind of information carrier, though the graviton itself is not exactly linked with these gravitational waves, because even if the sun and the Earth are stationary to some degree, you still have some kind of gravitational interaction between them. Yeah, I'm not positive how to answer it, because there is information carried in these gravitational waves, but my understanding is you still need some kind of force carrier to be able to have gravitational information transmitted from one object to another.
Yeah, what information do gravity waves contain that you've observed? And again, in the normal use of gravity, the normal occurrence of it, what's the link between gravitational waves and, again, just the normal everyday gravity that we experience here?
Yeah, so I mean, if you believe Einstein's theory, which is withstood the test of time for 100 years, then anything that's moving through space, is emitting these gravitational waves. The main things that we've been learning from these signals, because we're not able to learn about gravity on the solar system scale, for example, with gravitational waves, because anything in the solar system is not nearly extreme enough to be emitting strong enough gravitational waves for us to see. But the aspects that we've been learning is we can test Einstein's relativity in a regime that's impossible to create at a lab here on Earth or in our solar system. So we're able to see if Einstein's theory holds up for these very extreme systems that are moving relativistically near their merger. And so far, general relativity has withstood those tests as well. The things that I'm most interested personally are how these gravitational waves can help us understand the formation of black holes in the universe. So there are lots of theories of how black holes form and evolve in the environments they do. But really, the ones that we're observing with gravitational waves typically come from the deaths of massive stars. So by seeing the end point of the life of these massive stars, when these two black holes merge, when their remnants merge, we can extrapolate backwards in time to try to understand the intricate processes that happen during the lives of these massive stars. Massive stars are very short-lived things, but important for polluting our cosmos with heavy elements, for galaxy evolution, for cosmology. So this is giving us a new kind of probe into understanding the lives of these kind of behemoth stars and the processes that occur within them during their evolution.
Okay, very good. I don't know, what's the big goals of the observations currently? Is to observe like lower and lower frequency gravitational waves, or to observe them from non-cataclysmic events? Like, what are the big LIGO goals right now?
Yeah, totally. So right now we've only seen, like I said, we have about 90 systems that we've seen so far, but they only come from this class of events called compact binary coalescences. So CBC. So these are mergers of black holes and neutron stars. These were expected, and these are the easiest for us to detect because from Einstein's relativity, we have very clear predictions of what these should look like in our detectors, what the gravitational wave signal should look like in our detectors. So it makes searching from them not easy, but easier. A number of other possible things that might be giving us gravitational waves that we could observe from our current ground-based detectors are, for example, supernovae, when a supernova explodes, we know that it probably does it in an asymmetric way. So it's not a perfectly spherically symmetric explosion. And the movement of the collapsing core should give us gravitational waves. The strength and the signal of them is something that we don't have a great idea about. But that could help us learn a huge amount of the mechanism that happens when stars explode. The problem is supernovae only occur in our galaxy once every 50 to 100 years. And we can really only see these things with gravitational waves either in our galaxy or nearby galaxies. So we have to get a little bit lucky in that case. Other things we might be able to see are the signals of spinning pulsars. So you could have pulsars in our galaxy. These are neutrons that are highly magnetic and rapidly rotating. And even though they're so dense, they can have little mountains on them. And as that mountain spins around when the neutron star spins, it'll be emitting gravitational waves as well. So there are searches going on to find these things that we call continuous waves from these spinning pulsars. But really the big thing that we're doing now is every observing run that we have. So right now we're in a commissioning phase. We're going to start observing again in late 2022. But every observing run, we're increasing the sensitivity of these detectors significantly. And when they turn back on, it means that we're going to be seeing more and more and more of these events over the time period that we're observing. So with 100, we're starting to really have the basis of a population that we can get a better understanding of all the evolutionary processes that lead to black hole formation. But in the next few years, we're going to have hundreds, if not even 1,000. And in 20 years, we can have hundreds of thousands of these events that we can start to understand. So it's really kind of a numbers game is a big part of it as well. And when you have larger numbers as well, you have a better chance of seeing kind of the oddball events that could really help you understand new physical processes and things like that as well.
Excellent. So, Mike, what's the best way for people to find out more about your work and about LIGO in general?
So for my work, you can either follow me on Twitter. It's at Space Don't Wait, or you can go to my website, michaelzevin.com. For LIGO in general, there are loads of different social media things that LIGO has. So you can follow LIGO on Twitter. And if you're interested in playing with the data itself, all of our data is public. So you can go to the website GWOSC.com. That stands for Gravitational Wave Open Science Center. So GWOSC.com. And download the data for yourself if you're interested in playing around with it. A lot of other groups outside of LIGO have created their own search algorithms and have found a number of new events that weren't found with the LIGO algorithms themselves. So there's lots to be done as far as the searching for these things within the data itself as well.
Excellent. Well, it's been a really interesting call. So, Mike, thanks for coming. I appreciate it.
Yeah, thanks for having me.
Remember, before you go, supplementing with hemp CBD products is one of the best things you can do for your well-being. Get your CBD from a company that cares and offers you holistic support in your healing or wellness journey. Feel Good Hemp is giving our listeners 33% off their first purchase. You can use coupon code GENIUS33 at checkout to save 33% site-wide. Visit feelgoodhemp.org to shop now and access their free empowerment platform.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.